Welcome back from break. I'm Mark Marley from the Lunar and Planetary Lab at the University of Arizona, and I'm happy to welcome you to our panel discussion, which is determination of stellar properties from observations and models and the classification of young stars. And it's so important in understanding the disk evolution, understanding the planets that form afterwards, to understand the ages and how the stars have formed. And so this panel is going to talk about both the observational side and the theory side of this. And our four great panelists are Lynne Hillenbrand from Caltech, Chris Johns-Krull from Rice University, Isabelle Baraffe from the University of Exeter, and Greg Feiden from the University of North Georgia. And the way we're going to work this is each panelist will talk for about 7 or 8 minutes, just sort of summarizing the longer talks for those that have them up on the YouTube channel and giving some of their thoughts on this topic. And then we'll open it up for discussion. So feel free to enter questions in the Q&A chat, and be sure to upvote the questions that you think particularly resonate with you, and that'll help me sort through them as we have the discussion session afterwards. So with all of that, let's get right to it, and we're going to start with Lynne Hillenbrand. And so go ahead, Lynne, you've got about 7 or 8 minutes.
Great. Okay, I think I can share a screen and hopefully you can hear me. So this is a quick summary of a longer talk that is on the YouTube channel. And what I wanted to touch upon are some of the things that we've heard about already from our morning panelists. So in particular, Tom McGath told us about protostars. And so these are very dynamic systems. So we have an accretion disk, material comes in, some of it's ejected in an outflow, some of it winds up on the central star. And what I want to talk about is how we know the properties of this central stellar object and some of the complications that we have in doing that, because these are young accreting objects, at least for the first several million years, as we heard. And so this picture zooms in a little bit to this. And again, what we're interested in are the properties of the central star, which in the upper left panel here is showing a spectrum where we have nice absorption features that let us classify this as some kind of K or M type stellar photosphere. It gives us some information about the temperature. But when we have this dynamic accretion system, as that rate of infall of material from the disk onto the star increases, we have an increasing presence of emission lines at the short wavelengths, as well as some continuum excess that causes the colors of the star to become bluer, particularly at the blue wavelengths. And then we have some contribution from the disk that causes excess at the red wavelengths. And so again, trying to figure out what the properties of the central star is complicated by all of this material. And so, we use the observations both to learn about the inflow and the outflow processes through these various emission line diagnostics. But again, to determine the properties of the star, we really need to figure out how to distinguish that from the bulk picture that we get from our photometry and spectroscopy of these young systems. And so what do we want to know? First of all, a very fundamental characteristic is the temperature of the star. So just as a basic radiative property, how hot it is. And in the context of planets and young exoplanets, particularly hotter stars have more ultraviolet emission. There can be, also chromospheric activity, as we'll hear. So the temperature and what we're seeing, what physical processes we're seeing at different wavelengths help us in understanding the overall radiative properties, that impact the disks and the planets. And then another thing we'd like to know is the luminosity of the central object. And this is just an integrated brightness over the spectral energy distribution. But as we've again heard, there's excess emission in the optical and ultraviolet from the secretion process, and excess emission in the infrared from the disk processes. So determining the underlying luminosity again is a challenge for these reasons. So these are radiative properties, temperature and luminosity. We're measuring something about the emission coming from the star. as well as the circumstellar environment. But fundamentally, what we'd like to know is the mass of the star and the radius of the star. And these are important, again, in the context of exoplanet studies, because we often measure fractional properties in some way. So M2 over M1 of a planet, for example, or R2 over R1. And so knowing the radius and the mass of the star helps us or is critical for determining the properties of the planet. And then a big one is age. And we've already seen some this morning, but I think we're going to see lots of plots throughout the week about some parameter as a function of age. And keep in mind that the age estimates are quite uncertain. So let me just illustrate. I'll go through some of this quickly because, again, it's the long version of the talk is available. But when we look at one of these star forming regions, we try to survey, take photometric and spectroscopic data to uncover the underlying, or to uncover the stellar population that has formed there. And there are all kinds of reasons for aspects of star formation studies, how stars form out of molecular gas, how they evolve in the HR diagram, for example, what the initial mass function is, how long the star formation process takes. So there are many reasons that we want to know these just for the stars, not in service of exoplanets, but I recognize that's the application today. But we've been able, through the bounty that has come from Gaia, to determine parallaxes, which give us distances. So that's critical for placing stars in the HR diagram and learning something about their physical properties. We have fundamental distances now, which is, to me, amazing to see how this has evolved. And then, as we've heard this morning from Jonathan Gagne's talk, also the clustering and two-dimensional kinematics of, he was talking about open groups, but we can also do this for younger star-forming regions as well. So here's an example where there's subclustering of the stellar population and some inference about the kinematics of these individual groups. And again, how stars are forming here in space and time. And in particular, we get some estimate of ages now from kinematic properties of these young clusters, as we've heard. But then there's also the large surveys that have taken place, these multi-wavelength surveys from optical to near infrared to mid-infrared wavelengths that have filled in photometric information. So we can measure spectral energy distributions, measure the disk excess, measure variability properties, which come into how we know the fundamental properties of stars, and then also spectroscopy, from which we get a wide range of detailed properties about the central star and the accretion processes. So these are the measurables and what we can infer from them. What we would like to do is look at again the star formation histories. And in order to age date stars, we use the HR diagram, and we'll hear again more about this as this session goes on. But two of the mysteries in these HR diagrams, and they're long-standing, are that the empirical isochrones and the theoretical isochrones are not matched well across a range of masses, from low mass stars to higher mass stars. And here, there's a systematic issue here that has to do likely with accretion histories, and I think we'll hear more from our other panelists about this. But then there's also a longstanding issue of the luminosity spreads and whether they correspond to age spreads, or again, differences in accretion history between different stars. So empirically, we try to do a good job placing stars using both of these axes, the effective temperature and the luminosity. And our measurements are getting better, and our ability to do this is, as we take into account all of these effects, is getting better. But these, what I call irritating luminosity spreads, have not completely gone away yet. And ages, and that's what's shown here as these isochrones. And as I said, there are these mismatches between the empirical isochrones and the theoretical isochrones. Yet the HR diagram remains an extremely powerful tool for determining these properties, namely masses and ages for stars. And so I'll just skip through because I suspect I'm running out of time already. But this is just a flowchart illustration of how we do this, the different spectroscopic and photometric criteria and the steps along the way that we need to account particularly for the accretion of young stars in order to place them well and determine the accretion properties and the extinction properties, so as to get, again, a good measure of the luminosity. And just to be clear about these complications, as I said, they're active, they have dust and gas, which complicates things. And one major issue is the variability of these young stars, and the fact that they're variable at all wavelengths, having to do both with the underlying spottedness, the chromospheric activity, as well as any superposed accretion effects. So this also needs to be taken into account when we consider how to determine the properties. And these are just some illustrations of what this excess is and what the variability aspects are. And I should probably stop here and let others have their say. But these are the complications, and I'll just skip to a concluding slide here about things I think that we could discuss in our panel discussion. So I will stop there and let the next person.
That's great. Thanks, Lynn. I've learned a lot from you and listening to your talk about what some of these uncertainties are. Let's hear next from Chris Johns-Krull from Rice. So go ahead, Chris.
Okay, thank you very much. Everybody, you can hear me okay?
Yeah.
All right, thank you. So I was asked to speak a little bit about sort of the uncertainties and the robustness of spectroscopic analysis, and I took that to mean high resolution spectra. That's mainly what I've worked on. And there is, I think, certainly an impression in the community. One of the things that we always say is that if you go to high spectral resolution, you can learn more about the star, and you are perhaps not affected by some of the things like extinction, reddening, and other things that might depend a little bit more on the circumstellar environment. So as Lynn was saying, there are a number of things we would like to know, effective temperature being one of the primary ones because that places things in the HR diagram. We do also want to know how fast these stars are rotating, so V sin I. We'd like to measure their gravity because that tells us something about their mass and radius. The little r here is the veiling. And we'd also like to know about their magnetic field. And in the best measurements, we can independently measure the magnetic field strength and its filling factor, and then perhaps also the composition. Now, I must say that most studies don't really try to measure the composition. They assume a solar metallicity, but the few that have tried generally get around solar metallicity. But many of these other things are available both from optical or near infrared, high spectral resolution observations. Shown here is a spectroscopic study that shows a main sequence star, GJ380, and a classical T-Tauri star, BP tau. And you can see the lines look different in a number of ways. So the width, for example, of these CO lines down here can tell you about the V sin I, the rotation. The wing shape of these strong lines like sodium and aluminum can tell you about gravity. The width of these titanium lines, for example, compared in particular to the CO lines, can tell you about the magnetic field. And then the overall strength of the lines can tell you something about the temperature, the veiling, and other things. So these are the things that we would like to be able to do as a detailed spectroscopic analysis and fit some of these observations to determine the stellar parameters. Now, when you do these spectroscopic analyses, I just want to emphasize that you generally have to tune the line parameters. If you go to any random database for spectral lines and just pull down the lines and compute a spectrum, I've done this for the sun and compared to the solar atlas shown in black, there's generally good agreement, but there are some lines that are completely mismatched. And as you go to very different spectral types, these mismatches can be more dramatic. And so if you don't take the time to tune these spectral lines, and what I mean by that is to determine empirical oscillator strengths and van der Waals broadening terms, you can get very biased and sometimes inaccurate results. So in terms of some of the most recent studies, large-scale studies have been done in the infrared as we have better and newer high-resolution spectrographs that get a lot of wavelength coverage in the infrared, so it shells. And this is sort of showing you, for at least this one star in this large study by Lopez Valdivia, the general uncertainties that get associated, the accuracy associated with the various parameters you're interested in. So temperatures in the neighborhood of maybe 90 to 100 degrees effective temperatures, gravities maybe in log G in the neighborhood of 0.1 to 0.2, magnetic field strengths around 0.1 kilogauss, that's in units of kilogauss, V sin I's in the neighborhood of 1 or so kilometers per second. And veiling measurements, this is the infrared veiling, which is the disk emission relative to the stellar emission, coming in maybe 0.05 or so as in terms of the accuracy with which you can make these measurements. Now, if you don't include the magnetic field in these analyses, you do bias your results. The results are perhaps not for any one star, not too large, but you do get a systematic shift in things like the effective temperature, in the gravity, in the veiling, and in particular in the V sin I, because most of the lines, particularly in the infrared, are magnetically sensitive unless you're dealing only with the molecular lines like the CO lines. So what are some of the outstanding issues? I was asked to think about these, and I think one of the main issues just from the observational perspective is the spots. We believe that these young stars, we know that these young stars have very large star spots on them, and that manifests itself in a number of ways, but one of them is if you look at sort of detailed optical spectroscopic studies to determine, say, the effective temperature and compare it to infrared studies, generally speaking, the infrared studies find about 300 degrees cooler for the effective temperature. And that's almost certainly because once you're out in the infrared, in the K band, you're being dominated, your light is starting to be dominated by the cool component, whereas in the optical, your light is dominated considerably by the hot component. Now, I've done kind of an extreme case here where the hot component is 25% of the star, the cool component is 75% of the star. But we do know from Doppler imaging studies and other studies that these stars have, in some cases, very, very large spots on them. In fact, maybe the poster child for this is a study that Gully Santiago did in 2017 on lit calcium-4, where they came up with 20% of the star at 4100 Kelvin, 80% at 2750 Kelvin. So that would correspond to an effective temperature of 3180, whereas again, the optical study said the effective temperature was 4100 degrees. So if you just take this at face value, that puts a big change in the radius, a big change in the mass, can affect the mass accretion rates that you derive from this. So this is an area I think needs some considerable look and study. And you might want to use ways to test these results. One way you can do that is comparing things in the HR diagram. So this is showing an optical versus infrared determination of the effective temperature of BP tau, for example, and comparing it to pre-main sequence tracks without a magnetic field or with a magnetic field from Greg, who's going to talk in just a little bit. And the masses you infer depend quite a bit on whether you're going with the optical temperature or the infrared temperature. But we do have a dynamical mass for this star. This is one of the stars that has a disk around it that ALMA can give us a mass. And we know the mass of the disk is about 1.1 times the 1.1 solar masses. So these are things that I think that we do need to worry about. And then the other thing I would just say is, what is the actual effect of the magnetic field on the photospheric structure? When we do the spectrum synthesis, we need a temperature structure for the star. We know the magnetic fields on these stars are very, very strong. They are stronger than equipartition. The atmospheres of these stars are governed from a pressure point of view by their magnetic fields. Some Doppler imaging studies get very strong meridional and azimuthal components. So there's going to be some magnetic support for the atmosphere that has to change the temperature structure of the atmosphere. And basically all of the models, all the synthetic spectra we calculate are assuming no magnetic field in the actual atmosphere when we deal with the actual thermal structure of the atmosphere. That's got to have some effect, and it's really not well studied. So I will end there and look forward to what our next speaker has to say.
Thanks very much, Chris. That's a great summary. And next up is Isabelle Baraffe from the University of Exeter. So go ahead, Isabelle.
Okay, so let me share. Okay, can you hear me? Can you see my slide? Okay, great. Yeah, okay, so good morning, good afternoon, good evening. I will just summarize what I've been talking about. So my talk was about stellar models and atmosphere models. and from the modeler point of view. And here, because I give the details in my talk, I will just be very brief. I want to give a chance for discussion. So in my talk, I've tried to identify the main uncertainties which are the most relevant for this workshop. And I've identified three main uncertainties regarding models, that is for evolutionary models, but also atmosphere models. So to comfort my dear chairman, I have three problems, and therefore I have three slides. So the first problem I've identified is the uncertainty of stellar models at very young ages. I mean, this is a kind of a thing that we all know, but it's a reality, and a reality we have to live with. And this brings us to the problem of initial conditions, which means that when we have a stellar evolution model, what is the t=0 time? And this is a question. So I raised the question in my talk. If you follow it, I don't have real answers. They are solutions. One of the solutions is to account for the history of the star formation process, which means accounting for accretion process, for example. But this is very uncertain, as we know, which means that we have to continue and pursue our efforts to build a consistent picture between the molecular cloud collapse, between the evolution of disk, and between the early protostar evolution. So that's a big challenge, and we can talk later about that. It's a challenge, but I think it's an exciting problem, and we may progress in terms of knowing better the initial conditions and maybe what is the t=0 time. So my second uncertainty, I would say, which is important, is about non-standard physics. And when I say non-standard, I'm talking about rotation and magnetic fields. And it is good because Greg Feiden will talk after me and discuss that. So we know, as has been highlighted before, we know that models with magnetic field can actually explain better some overluminous objects, which I show here in a Hertzsprung cell diagram for young clusters. So does that mean that we have to use those models, those non-standard models? Yes, certainly. But the problem is that we have to be aware that those 1D models, stellar evolution models, actually rely on phenomenological prescriptions of 3D effects in the interior, which are extremely complicated and still need to be validated. So there is a sustained effort from the current stellar MHD community, and I think we still have to be a bit patient to learn a bit more really about what the magnetic field is doing on the interior structure of low mass objects. And here a message which I think there is effort to do from the modeling point of view, but in terms of observations, it is absolutely key to gather multiple information, which is not only the spectra and the magnitude, but also information about the activity, about the rotation rate, about lithium abundance, and about the cluster memberships. So now we need to have all those type of information to try to progress. And my final point, which is not necessarily linked to, I would say, stellar evolution models, but is linked to atmosphere models. And I think this is crucial here, specifically for this workshop, because we are interested in trying to characterize an object from its formation process. And therefore, I will talk about the signatures of formation for planetary mass objects. And there is here a problem that is known by modelers and observers, which is that non-equilibrium chemistry processes can mimic the signature of non-solar metallicity. And for example, just to illustrate that, I gave some details in my talk. We know that in a synthetic spectra, if you increase the metallicity by a given factor, you increase the absorption feature by CO. But if you include non-equilibrium chemistry, then you can get the same type of signature. And this makes, of course, I would say, the problem of determination of metallicity of an object versus kind of intrinsic chemical processes quite difficult to disentangle. And there, the modelers have to work and to do systematic exploration in order to find the sweet spots in the spectra to try to distinguish this metallicity versus non-equivalent chemistry. And the problem is complicated because in the models, there is a free parameter, which is the KZZ, the famous KZZ parameter, which characterizes vertical mixing and which is essentially a free parameter. And from my point of view, this parameter should be calibrated through hydrodynamical simulations, but not through observations. And I will stop here. So that were my 3 points, and I hope we'll have some time to discuss them. Thank you.
That's great. Thanks, Isabelle. Thanks for being concise. And our final panelist is Greg Feiden from the University of North Georgia. So go ahead, Greg.
Just a moment, I'm getting.
I hear you, but I don't
There's
see
a
you.
security issue with Mac that for some reason just popped up. Right, here we go. Okay, so can you see the screen all right?
Looks good.
Perfect, great. So I think a lot of what I had to or would have to mention has been covered extensively by Lynne and Isabelle in both of their talks, which I encourage you to check out as soon as you have an opportunity. But I was asked to speak about the challenges of modeling young stars and kind of what we can do to help relieve some of those challenges. And the biggest challenge is that our models aren't very good, they're fairly inaccurate. And trying to figure out why they're inaccurate tends to be the more difficult problem. It turns out young stars, if there can be something wrong with them, or there can be some interesting physics to modify what they look like, it's usually going on with young stars. So they have convection, which is notoriously difficult, not just for young stars, but for all stars with convective envelopes. They rotate, they have magnetic fields, they have star spots on their surface. They have accretion, potentially active accretion, depending on what age you're looking at, but also the properties of the stellar models can depend on the history of accretion. So we might have to somehow figure out the accretion history, which seems rather difficult to do. There are interactions with the disk, and then potentially if you're dealing with binary systems, there could be different dynamical interactions that can inject energy into the star and potentially cause some interesting things from there. So there's a whole host of different phenomenons, some of which are important at very early ages, which for this workshop is kind of where we're most interested in the planet formation era. So disk interactions, accretion history, dynamical history all matter in the planet formation era potentially for the properties of your star, but then the magnetic fields, convection, rotation, star spots kind of matter always, no matter what age you're looking at. They can potentially play an important role. And so the difficult thing is that these are all three-dimensional, complex three-dimensional processes that we as modelers are trying to kind of pare down to one-dimensional prescriptions, as Isabelle mentioned a couple times. And that's just a difficult task, and knowing whether or not we're doing that right is extremely challenging. And then all of this is subject to the underlying physics that have to be right before we can start thinking about all of these additional physics. So the equation of state, the radiative opacities, we kind of have to make sure we have everything in order, and teasing out all of those small differences or small errors can be extremely challenging for young stars. And so what we want are a set of stars or certain stars or a group of stars whose fundamental properties have been really, really well determined. They've been well studied, well characterized. These are what we would call our benchmark stars or benchmark systems. And they're needed to validate these benchmarks are needed to validate the model physics so that you, a user of stellar models, can ensure that the predictions from the models are accurate, and you can infer the mass of your star, the radius of your star, whatever property it is that you might need for your disk or exoplanet studies. And so if you think that, oh, I'm not interested in the stars, I'm interested in the planets, you kind of need to be interested in the stars if you really want to figure out what's going on with your system. And the number one thing that we need as stellar modelers is stellar masses. We need stellar masses. Stellar mass is the single most important property that anyone could measure of a star if we're interested in assessing model physics. And that's because models predict the luminosity, radius, the temperature as a function of not just time, but also stellar mass and composition. You have helium abundance Y, your metal abundance Z, your mixing length parameter, and a whole host of other free parameters that kind of sneak in, and other physics that enter as well. And so the mass is really the main independent variable in all of these stellar models, and we have to give our models a mass to be able to ask what the properties of a given star would look like. So you have to measure a mass and then one or more of the other predictive properties, luminosity, radius, temperature, to get a direct test of model physics. And then the masses can help discriminate between the different physical ingredients, and we can get a better assessment of which physics are important and which ones you need to get an accurate assessment. Now, the goal as a modeler, I would say, please give me a mass with a measurement error uncertainty less than 2%. Most people would turn and laugh at you if you asked for that, just for kind of unanimous across the board. But the realistic goal is we need something kind of around 5% error in your mass uncertainty. If you're not within 5%, the models have too much freedom and the constraints aren't that great on the model physics if your masses are kind of uncertain to greater than 5%. And the same is true for all of the other measured quantities. We kind of want them into the 1 to 5% regime so that we can really pin down constraints on stellar models. Just as an example of the power of mass measurements, if you take just a single system, you plop it on an HR diagram, luminosity versus temperature, models, you can essentially choose what age the system will be, and then you can read off a mass here shown as black, the black thin lines. You would say that this system has masses of 0.2 solar masses. And without a mass measurement, you wouldn't know any better, but the mass is really about 0.3, 0.35 solar masses for this particular case. And so we find that models do a pretty poor job of predicting masses from placement on an HRD, which Lynne talked about extensively. And then Isabelle also mentioned that if you put stars on a mass radius diagram, adding a second layer of restriction, you find that models do equally poor. And sometimes in the wrong way. But adding mass measurements really places strong constraints and restricts the freedom of modelers to kind of choose an age to fit their need and to fit a solution. And then we can, I hope, and we get to talk about this a bit more in the discussion, is that having a mass allows you to start to distinguish between the effects of different types of non-standard physics that Isabelle mentioned, be it accretion, be it star spots, be it magnetic fields. Different stars of different masses are affected in different ways. And so how we see different stars or where we see different stars of different masses in various diagrams, HRDs, mass radius diagrams, et cetera, can start to place constraints on the types of physics that are moving them around. But we also would like to do this in clusters where we can relieve the age discrepancies and degeneracies. You get multiple diagnostics, lithium depletion, main sequence turn on, main sequence turn off. You get slopes of the HRD in the mass radius diagram. Hopefully we get a metallicity estimate. I encourage you to check out Trevor David's paper from 2019, where he did this with multiple eclipsing binary systems, where you have multiple mass measurements of multiple different systems to kind of really pin down models and say, you don't get to move. What are your predictions? Are you consistent? Are you accurate? And then as Chris just mentioned earlier, metallicity is important, composition. We normally don't talk about it. It's ish solar, but ish solar isn't always good enough. You change the pre-main sequence effective temperatures in models by about 50 Kelvin for every 0.1 dec in metallicity. So it can matter depending on how far from solar you are. And then we would also like to get magnetic field strengths. So as a modeler, my request is please measure everything about your star before you come talk to me. Not that that's actually the case, but benchmark systems, we really want to focus on getting very, very good, well-understood systems. Statistics are not going to be a substitution for carefully well-studied systems in this case. So if you're just hoping to get a mass of systems, it's not going to work. We need to understand a few systems really, really, really well. And I'll just leave some open questions here really quick as I wrap up. These are the things that kind of came to me just preparing for the talk today. How inaccurate are models as a function of age? What physics are missing? Are they important? Are we just turning knobs? How reliable are our physics, as Isabelle mentioned, both in the interior and in the atmosphere? How reliable are our radiative opacities? Do magnetic fields affect atmospheric structure and the atmospheric chemistry if you have high energetic photons streaming around? And then we often use binaries as our calibrators. And for the observers, I'm always wondering, are binaries actually representative of single stars, or are we just using poor or wrong calibrators to try and assess the model accuracy? Thanks.
Okay, well, great. Thanks to all four of you for kicking off the discussion. Let me ask, in listening to all these, I have a question maybe we can start off with. And I was kind of struck that I think all of you mentioned accretion history as being such an important unknown. And we know from just the experience with the solar system, thinking about solar system planets, that we explain so much by one-off stochastic events, like the moon forming impact of the Earth produces the moon, but Venus doesn't have a moon, or the Uranus is tipped on its side, perhaps from a giant impact. And so it seems like so much could be tied up, thinking now about the star and the accretion history. And so I'm curious, what does accretion history mean to each of you? I mean, it's the history of mass accretion over time, but is there anything else tied up in there, like the angular momentum or the dust or anything else? So what is accretion history really? To a modeler. Isabelle, do you want to?
Yeah, so, okay, so for me, I say, what is accretion history? That is what is impacting the evolution of the structure of the objects. So this is not only the accretion rate, which means, an m dot as a function of time. And so this means that you have somehow to follow that from the very beginning of the formation of the pre-stellar core to the end of the process when you reach the final mass. But accretion history means also to have some kind of knowledge of the amount of thermal energy which is accreted on the central body. And this is even worse, I would say, in terms of uncertainty compared to the accretion rates, because accretion rate can be either measured or can be inferred from, I would say, molecular cloud collapse simulations. So at least we can have some knowledge, but this amount of thermal energy, which is accreted on the central object, this is really a difficult problem, because we need to have information about the not only the evolution of the mass in the disk, but we need also to have information on what we call the boundary layer, which is actually how the material is falling from the disk onto the material. And this is tough. So this is a big uncertainty. So this is what are important, I would say, for me, modeler. Yeah.
Anybody else want to?
I would just agree with that. And, as an observer, we're trying as hard as we can to, both identify these outburst events and measure, something about the properties in a way that is helpful. And the boundary layer issue is a confounding one for sure. But the other thing I'd like to emphasize, going back to what Greg was mentioning about the fundamental masses and radii, and it's related to accretion, because to go between an accretion luminosity and accretion rate, say, that relies on m/r, the mass of the radius and the stellar radius, having those fundamental measurements, I cannot underscore that enough, as Greg already mentioned. So those of you looking for transiting planets and you find all of those, boring eclipsing binaries out there, pay attention to them, because if any of them are young, they will help calibrate these tracks, particularly in the pre-main sequence phase. Obviously, they're valuable everywhere, but particularly in the pre-main sequence to help calibrate these tracks and isochrones, they're extremely valuable. And if we can get that at even younger stages, determining fundamental masses and radii for protostars or top of the convection track pre-main sequence stars, I think that's really where the next frontiers lay here. And if we have an infrared Gaia, maybe that'll be a big path forward as well.
Any other comments from the panel?
I guess I would just, add on to that how important the radii are, because that can start to give us a handle on just how bad, from an observational point of view, the spot coverage is, and how that then affects what we infer for the radius. If you're just doing, a luminosity and a temperature and trying to get a radius from that, if you're missing most of the light because most of it's spotted, that's a problem. But if you can do the transit or the eclipsing observations at a variety of wavelengths, that will let you actually get a better handle on the radius, what the actual radius is.
Well, this maybe ties into a question from the chat. Someone's asking about astroseismology. Can we do astroseismology on these young stars to help tease out some of these properties?
I would just say, I think it was Greg that said basically anything that can go wrong with a T-Tauri star is going to go wrong with a T-Tauri star. And I think that's going to swamp, particularly at the lower masses, the astroseismology signature. So I would be skeptical.
Yeah, that was my first thought, is that with astroseismology, it's a powerful tool, but there's a lot of noise if you look at a light curve from a young star. So there's a lot of variability going on. And in terms of assessing an age, I think the way that in astroseismology you usually assess the age is the amount of helium in the core compared to where you expected the star to have started. So you look at a fusion byproduct essentially, and we just don't have that with young stars. So I don't want to say it's impossible. I know there have been attempts to do it, but I think it's going to be extremely challenging to provide robust information about a lot of stars through these types of techniques.
I would just go ahead, Lynn.
I was going to say, that said, there have been some results that came mostly out of Corot in the more massive stars, which cross the classical instability strip on their way to the main sequence. So there is some astroseismology information, just not down in the low mass regime that we're mainly talking about, because that's most stars are low mass. There have been predicted pulsations from deuterium burning, for example, but thus far that has not been found observationally.
Okay. There's a lot of questions for Isabelle about the disequilibrium chemistry and maybe the ranges in which that might be important. Do you want to say a little bit more about maybe the big picture of what sort of temperature ranges where the disequilibrium chemistry matters, and where that's going to impact our understanding of the evolution and the metal?
Yeah, sure. Okay, Mark. Yeah, although you could probably better explain that than me. But okay, so this essentially concerns this problem of chemical non-equilibrium chemistry is more about the chemistry of CO to methane and to nitrogen. So this is really for cool atmospheres, typically for effective temperature below 2000 K. So here I'm talking about this problem more for planetary mass objects, not really for, I would say, stellar atmospheres. Stars are fortunately not concerned by that. And I think that the metallicity determination, because I've seen a question about that, metallicity determination for stars are, I would say now, very well advanced if they are still not accreting or affected by strong magnetic fields. But in this case, I would say that stellar spectroscopy is quite advanced with 3D models, etc. So it's more this problem about non-equilibrium chemistry concerning those, I would say, it's the range of L to T to white dwarfs. And it's really not for characterizing the stellar metallicity, but for characterizing the planetary mass object that you are directly observing. And so that is the problem.
Since you mentioned the brown dwarfs, there's starting to be some indication that the spectral type or the effective temperatures you derive depends on the viewing angle, because the heat flow or the atmospheric structure or the clouds is different at the equator from the poles. Have there been any evidence for that in the young stars, that some of these properties that are derived against the models depend on the inclination that we're looking from?
I don't know, maybe in the same way, but the young stars in almost all Doppler imaging studies of the young stars show strong polar spots, right? So the viewing angle is going to affect the amount of the star you see that's covered in spot, probably. And so that's almost certainly going to affect what you derive for its properties, even, but I would say most, there aren't that many really rapidly rotating stars that you can do the Doppler imaging studies on. And then when they become so rapidly rotating, a lot of our spectroscopic techniques to determine all these other things get messy just because the lines get so broad. But polar spots are common. You would expect that to affect the parameters you derive.
I'm not sure people have looked for that, but it's a good experiment, and it does require Chris's high dispersion spectra.
You all haven't said a lot about JWST and how that's going to be impacting this field. Any thoughts on what we should be looking for as some of the low-hanging fruit that JWST can uniquely do?
I'm looking at Lynn.
Yeah.
It's not going to give me my high resolution spectra, I can tell you that.
Yeah. Lynn, do you have any thoughts, or?
I guess you know, some interesting experiments would be getting back to the fundamental masses issue of getting binary orbits for protostars, for example. That doesn't give you unique masses, but some constraints on masses, and from protostellar binaries, I think would be interesting.
Okay. Thank you. We have a question about, from discussion of the magnetic fields, what happens, someone is asking, as the star turns onto the main sequence, what's the holistic way of thinking about what happens to the magnetic field as we get onto the main sequence?
Well, from an observational standpoint, I'll just say that we expect that the magnetic field will, combined with the rotation, will drive a wind. And you will have stellar mass loss that will slow the star down, and the magnetic field in the star itself is produced by a dynamo process that is going to then become less and less efficient as the rotation slows down. And so we expect the magnetic field to become less important, less strong, less dominant, and that I think would then affect the modeling structure, and I'll let Greg take it from there.
Yeah, I mean, I think that's the general picture, is that you start out with young stars being extremely active, and then as they kind of slow their rotation, we see that their activity levels go down, and so presumably the strength of the magnetic field goes down as well. And I think there's some evidence for that from different studies of Zeeman Doppler imaging studies, for example, can try and get an estimate of the magnetic field strength. And we find that it decreases towards the main sequence for more solar-like stars. And then if magnetic fields affect the interior structure, as I would say that's a big if, then you might expect that would happen as well, that somehow maybe young stars are more affected by magnetic fields or the magnetic activity, and then by the time you get to the main sequence, hopefully you get to stop worrying about it. I'm not sure you do. I'm not sure you don't. So it kind of, the magnetic field maybe becomes just less important overall in terms of the characteristic of the star.
Okay, thank you for that. I'm looking at the questions. There's a lot of thoughts. I think we've covered a lot of the questions about spots. There's some discussion about, do these spots impact transit methods? And I think as we've heard, there's so much variability in these objects that they're really not well suited for looking for planetary transits. And Carl showed the nice table showing that for these young ages, the vast majority of objects have been detected by direct imaging. So thinking about this and thinking about, again, the upcoming observational capabilities for the planet detection portion, and the 30-meter and the capabilities we'll get from 30-meter telescopes, where do we think the best or the best pathways for detecting planets around these systems is going to be, and at what ages do we think the different methods would work best? So direct imaging younger than 10 million years, 20 million years, is there a turn on for when we can start to think about other methods?
I think that's one place where JWST will help a lot because of the resolution that it's going to give, and at least certainly at these young ages, particularly for the higher mass planets, they are brighter relative to the star than they would be at much older ages, and so I think the hope is that we will be able to image them even closer in than the current group of directly imaged planets have been found. And then I also think just going to longer wavelengths in general for a lot of our methods, both for the radial velocity and for the transit method, the variability is still there, but it's less severe typically as you go to longer wavelengths, particularly once you get rid of the disk, once you get past the stage of disk accretion. So, so I think those are where the sweet spots are, but it's not going to be easy.
Any other thoughts? Well, I think we've gotten through most of the, there's a lot of overlap between the questions, and just taking a look here, I think I've covered the majority of these. Maybe
there's a prompt to talk about luminosity as a function of time and how that affects forming solar systems.
Okay, why don't you take that one?
Well, okay, maybe one of the theorists should take that one, but you know, the obvious the implication, though I don't think many of us really showed, you know, a pre-main sequence star contracting, but the obvious implication is that there are changes by orders of magnitude in the luminosity of the star as it's falling from the top of its convective track, you know, down onto the main sequence. So luminosity changes by several orders of magnitude, and that obviously changes the radiative field for young planets. And then the challenge, particularly in very young stages, is that there can be these accretion-driven outbursts, which both, you know, change the path, possibly change the path of the star through the HR diagram, but also, you know, impute a lot of flux luminosity onto these disks and planets. And, you know, that is something that's not well understood. And so there are two competing interests here, right? One is, you know, understanding stars and stellar evolution, and the other is the impact of the craziness of the young stars on the forming planets. So there are these luminosity changes, both, you know, gradual over millions and hundreds of millions of years, but also, you know, these short-lived events that could be, you know, brief, weeks or months or centuries even, where we have these big luminosity increases. So that's kind of outlining the problem without saying anything quantitative, but maybe our theorists can fill in.
And it's certainly a big concern, right, for the habitability of M-dwarf planets, which have to be in close to be warm enough, but they've experienced these very high luminosity periods. And so the question is, has all the water been baked out, or do they have ways of getting the water later? But other comments on Isabelle? Do you want to?
Yeah, just to follow up on Lynne's point, I think those objects which have kind of strong outbursts, like the FEORI objects, is kind of a category of young objects with very large accretion bursts. They are very instructive in the sense that they can tell us a lot about the impact of accretion, large accretion, on the structure of an object. And therefore, I could wish actually to have more. I know they are quite rare, but having follow-up of those type of I would say weird, strong accreting objects could be, from a theoretical or modeling point of view, very interesting. Just because they're kind of extreme, but they tell us a lot about what's going on when you have this type of strong bursts. So they are interesting, definitely. Yeah, they can tell us a lot.
Anyone else?
I guess
well, you know, thinking about this kind of variability that, you know, that has Lynne had some nice slides, and you had objects which show these outbursts and some that are more and more and more quiescent. What do we really know at the longest time periods? I mean, we're limited by how long we've been looking at some of these sources, but do we know, can things be active for 10,000 years and then turn off for a while? I mean, what do we understand about the longer term variability?
Well, our observations, our best observations go back decades, right? Not, hard on occasion, 100 years, but, most of the monitoring that is truly long-term is on the decades timescale. And, what's emerging from the variability studies is just the continuum of properties of these young stars, as has been said, the activity, we don't see, every once in a while there's a rise and an exponential fall off, a flare, right? That happens, like the sun and stars younger than the sun, certainly. But in these very young stages, the behavior is much more chaotic. And, there's everything from the examples that are in the slide deck from the work of Anne-Marie Cody primarily that show, quasi-regular bursting behavior, as well as more, stochastic kinds of events. And that's just from the high time resolution observations that we've had from Kepler K2 and now TESS. But to go to the longer time scales, right, we have much less frequent sampling. And so you're mainly sensitive to looking for larger amplitude, longer time scale kinds of behavior. And there too, there's just a continuum of features where sources could burst for a month, a week, a month, a year, several years, tens of years. And we're only now, I think, starting to appreciate the decline phase of some of these more interesting objects. So sources that were, these kind of famous outburst sources or well-known outburst sources have turned off and have declined, and people now notice these things, whereas also a lot of young star crazy behavior was going on and no one was monitoring, no one noticed. Now there is more monitoring of the sky going on. So we're developing our understanding of these statistics. So there's not a clean answer. I would just say there's a continuum of, turn on and turn off behavior in terms of these bursty events.
Yeah, I guess that's what I was getting at is can you extrapolate out the statistics to longer and longer timescales? But
I think Greg had something to say here too.
Okay, go ahead.
Well, I think I was going to just say now, Lynn, you mentioned this just now, and then Mark, you mentioned this earlier about the stochastic nature of a lot of the events and the phenomenon occurring on these young stars. And maybe this is a question kind of for everybody. Is what are we expecting in terms of understanding the properties of these stars from my perspective, from models? And is it realistic to think that we could take, a star or a given set of stars and actually be able to accurately extract the properties, kind of knowing that there's a lot of these other murky physics stochastically randomly happening, if that makes sense?
Well, I hope that we can understand the ones that don't have disks, and then presume that the stars that do have the disks are much the same. But then to know the accretion history, I think we're going to have to look at that probably as a more statistical process, and that may not actually fully satisfy you or Isabelle in terms of what you need to know to do the models correctly.
Yeah, I think there is one thing from the model point of view is that we realize there is a lot of uncertainty on the evolution of the accretion rate as a function of time. But in terms of the very structure or very impact on the structure, what is important is at the end, the total amount of mass which is accreted. And there will be impact or not depending on whether the accretion timescale is going to be shorter or longer than the thermal timescale. So I give that some details in my talk. So it's possible to, even if it's very complicated, to have a global picture with some kind of global approach where we do not necessarily need to go into very, very details, because I think this would be just impossible. But to have a kind of idea, when is an object gaining 90% of its mass? Is it during the first 10 to the 5 years of its life, depending on when you put t equals 0, or is it during the first million year? I think this is an important question. And we do not necessarily need to go into very, very, I would say, dirty secrets, of the accretion rate as a function of time. It's more about, okay, what's the global amount of mass accreted, and typically on which time scale? And I think this is probably accessible with observations through observations of a lot of objects. So things are not desperate. We can get to it. Yeah, I'm optimistic.
Well, I mean, maybe on that optimistic note, we should wrap this up. It's been a very interesting conversation. I thank all four of the panelists for illuminating this topic, and we'll leave it there. And I neglected to see what the next item on the agenda is. We're going to have a break, I see, and then at 11:45 Pacific, the hands-on sessions are going to for disk models is going to start. So thanks very much again, everyone, for participating. It's great to hear from all of you, and everybody else will be back in 15 minutes.